Hello everyone. This is Professor Deepika from Department of Electrical and Electronics Engineering of Sai Vidya Institute of Technology. In the last video, we were discussing about the derivation of the specific energy output and the power output and the factors which are affecting the specific energy output and the specific energy consumption. So in this video, we are going to discuss about some of the problems which are related to the mechanics of train movement. So that we will discuss one by one. So that is problems on mechanics of train movement and the problems on specific energy consumption. So the first problem will go like this. Let's read out the problem and understand the problem. That is, an electric train weighing 200 ton has 8 motors geared to driving wheels. Each wheel is 90 centimeter diameter. Determine torque developed by each motor to accelerate a train to a speed of 48 km per hour in 30 seconds up a gradient of 1 in 200. The tractive resistance is of 50 Newton per ton. The effect of rotational inertia is 10% of train weight, and the gear ratio is 4:1, and the gearing efficiency is 80%. So this is the problem they have given. So let us understand the problem. That is, we have a electric train which is weighing of 200 ton. That is, the electric train weight is 200 ton. And there are 8 motors, okay, and there are 8 motors geared to driving wheels. So there are number of the weight of train is 200 ton, which is only a dead weight, and the number of motors used over here is 8 motor, and they have also given that the the wheels what we are talking about is of diameter 90 centimeter. The diameter of the wheels will be 90 centimeter. And we have to determine what is the torque developed by each motor. Okay, so we have to calculate what is the torque which is developed by each motor to accelerate the train to a speed of 48 km per hour in 30 seconds. So that is the maximum speed they have given, which is nothing but 48 km per hour, and the time of acceleration they have given, which is nothing but 30 seconds, and the gradient they have given, which is nothing but 1 in 200. That is G, what we are calling it, is the ratio they have given, which is nothing but 1 by 200, and the tractive resistance R is nothing but what, which is nothing but 50 Newton per ton. And the effect of rotational inertia they have given 10% of the train weight. So why actually they have given this data? Because we have to calculate the effective weight. So they have given that effective weight usually will be greater than the dead weight, and which is nothing but 10% more than the dead weight. Hence this will be very useful. And the gear ratio they have given, that is gamma, is nothing but 4:1 or 4:1, and the gearing efficiency, that is eta, is nothing but 80% or 0.8. So this is the given data, and we have listed out the given data over here. You can observe W is nothing but 200 tons, D is nothing but 90 centimeter. Let us convert it into meter, hence it will become 0.9 meter, and we have to calculate percentage gradient. Correct? So percentage gradient is nothing but what? Usually it is nothing but we are going to calculate for a track of 100 meter. Hence we have to multiply this ratio into 100 to get the percentage, which is nothing but 0.5%. And our train resistance is nothing but 50 newtons per ton, and the eta is nothing but gamma is nothing but 4, and eta is nothing but 0.80, and the number of motors here will be 8. So this is the given data. First, let us calculate equivalent accelerating weight of the train. So it is usually 10%, and also they have specified in the problem, which is 10% more than the dead weight. Then how do I calculate this? So please remember that. So effective weight will be calculated like this. It is nothing but W plus 10% W. Correct? So it is 10% more than the dead weight. Whatever the dead weight we are having, so up to that dead weight we have to add 10% of that. Hence it will become 10% more than the dead weight. Hence how do I write this? So W will be the dead weight, and 10% of W is nothing but what? Which is nothing but 0.10 into W. So then W plus 0.1 W is nothing but what? Which is nothing but 1.1 W, and W is nothing but 200. Hence it will become 220 tons. Hence you can observe here the accelerating what we are calling. So this will be greater than the dead weight. W is only 200 ton, and the accelerating weight WE will be 220 tons, hence it is greater. And maximum speed Vm is nothing but 48 kilometer per hour, and time taken during the acceleration period, so they have given here that is to accelerate a train will be in 30 seconds, so therefore it will be 30 seconds, which is nothing but T1. So what I have to calculate here, I have to calculate the torque developed by each motor. So therefore we have actually derived the torque equation in the mechanics of train movement, hence we will be using the same formula here. So first of all, we have to calculate the acceleration here, correct? Because the formula will also be consist of acceleration alpha. So how do I calculate alpha? Or to why we have to know means because in the formula torque is nothing but what there the FT, that is tractive effort, will also be there. Hence to calculate the tractive effort we will be using this step. So hence the acceleration, how do I calculate? So acceleration is nothing but what speed by time, correct? Hence how can I write it as, which is nothing but Vm by T1, because the time during only the acceleration I have to consider. Hence alpha will be Vm by T1, and Vm is 48, T1 is 30, substitute, hence we will get 1.6 kilometer per hour per second. And the tractive effort required, which is nothing but what, Ft. So what will be the formula for Ft? Ft is nothing but what, 277.8 omega E alpha plus 98.1 GW plus W into R. So this will be the formula to calculate the tractive effort. So let us write the formula, which is nothing but 277.8 omega, WE alpha plus 98.1 WG plus WR. Let us substitute. So you can see here W is nothing but 220, we have already calculated, and alpha also we have calculated right now, which is nothing but 1.6, and W again will substitute, G is nothing but 0.5 and R is nothing but 50. Hence we have got the answer FT as 1,17,000. That time only we can use this. In some of the problem it will be not given in Newton per ton, then we have to convert it into Newton per ton. So hence we have calculated F. So the total torque. So again, the formula is Ft into D divided by eta into 2 gamma. So let us substitute. Ft is nothing but 1,17,595.6 into distance is nothing but 0.9. Sorry, this is not a distance. It is nothing but the, don't confuse with this. This D is nothing but the diameter, and the capital letter D, which will be using in specific energy consumption formula and all. So that will be the distance. So please remember this. So here capital letter D is nothing but what? It is nothing but the diameter. Hence, we'll be using this formula. Hence, the total torque developed will be Newton per meter. So, so our job is not done because we have to calculate the torque developed by each motor, correct? So, this is the total torque developed by all the motors. So, how many motors are there? There are 8 motors. So, so the torque developed by the 8 motors is this much torque. But we have to calculate what is the torque developed by each motor. So, how do I get that? So, we have to divide by total, we have to divide the total torque by number of motors, which is nothing but 8. So therefore torque developed by each motor is nothing but total torque developed by number of motors, so which is nothing but 2067.1101 Newton meter will be the total torque developed by each motor. Hence we have calculated the problem. Hence we have calculated the torque. Like this we have to go on. So you can see here, to calculate the torque will be we will be requiring these things, that is we require the tractive effort required, and we require, and remaining all terms will be given. So to calculate Ft will be using this formula, and to calculate this we have to calculate first We, and also we have to calculate alpha, and all the remaining things are given in the problem. So like this we have to move on with the problem. So next, the problem will be like this: a 200 tons motor coach having four motors, each developing 6,000 Newton meter torque during acceleration starts from rest. If gradient is 13,000, gear ratio is 4, gear transmission efficiency is 90%, wheel radius is 45 centimeter, train resistance is 15 Newton per ton, and addition of rotational inertia is 10%. Calculate the time taken to attain a speed of 50 km per hour. If line voltage is 3000 volt DC and efficiency of motor is 85%, find the current during the notching up period. So this is the thing we have to calculate. So let us understand the problem. So the motor weight is 200 ton and there are four motors and each developing 6,000 Newton meter torque. So this is not the total torque, it is the torque developing by each motor. Remember, it is the total torque developing by each motor, and the gradient they have given, and the gear ratio gamma they have given, and gear transmission efficiency eta they have given. Wheel radius they have given 45 centimeter, but in the torque formula we have the diameter, so therefore we have to convert it into diameter, that is 45 into 2, which is nothing but 90 meter or 90 centimeter, which is nothing but 0.9 meter, and R is nothing but 50 Newton per ton, and additional rotational inertia they have given to calculate the equivalent weight, and we have to calculate what is the time which is required to attain a speed of 50 km per hour. So therefore Vm speed they have given 50 km per hour, but we have to calculate the time over here. And the line voltage is 3000 voltage DC, that is input voltage they have given, which is nothing but 3000 voltage, and efficiency also they have given 85%, and also we have to calculate what is the current during the notching up period, that is the acceleration period. So let us list the given data. W is 200 ton, B is nothing but 2 into 45.9 meter, G is nothing but 30 into 1000 into 100, because it is the it will be taking for 100 meter distance. Okay, so level run of 100 meter distance, hence we have to multiply by 100. So therefore it will be 3%, and R is 50 Newton per ton, gamma is 4, eta is 0.9, WE is, in the last problem I have solved for you, hence it will be 1.1 W, that is 1 plus 0.1 W will give you 1.1 W, which is nothing but 220 tons again. Torque developed by each motor, which is nothing but 6,000 Newton meter. So what is the total torque developed? Because the formula what we are having, the torque formula will give us the total torque developed by all the motors. So in the problem they have given for each motor, each and individual motor. So how many numbers of motors are there? 4 motors. If I want to know what is the total torque developed, then I have to multiply by 4. So that for 4 into number of, it is not that way, 4 into the torque developed by each motor, which is nothing but 4 into 6,000 will give you 24,000 Newton meter. And hence the tractive effort, which is nothing but Ft is equals to what? 277 point, because that we can't use, because the time and all we don't know, that is the time T1 we don't know. Hence here the tractive effort given, hence we could calculate Ft, which is nothing but what? Because the torque formula we know that it is nothing but Ft into D divided by eta into 2 gamma. Hence I could calculate the Ft, which is nothing but eta into 2 gamma into T divided by D. Eta is nothing but 0.9 into 2, and gamma they have given here, you can observe the gear ratio, which is nothing but 4, and the total torque developed is nothing but 24,000, and the diameter is nothing but 0.9. Hence we will get 1,92,000 Newton will be the total total tractive effort. So why we are doing this term? Because we have to calculate the time T1, that is the time during notching up period or the acceleration period. So what is T1? Which is nothing but Vm by alpha. So I know Vm, correct? So I know Vm, but I don't know alpha. To calculate alpha, I'll be using this tractive effort formula. Hence, let us substitute the data over here. So Ft I know, We I know, alpha I don't know, G and remaining the things are known. Hence, the alpha is nothing but what? 2.01485 kilometer per hour per second will be the alpha. Now I can calculate what is the time during the acceleration period. So which is nothing but Vm by alpha. So T is nothing but Vm by alpha. 50 by 2.01485 will give you the answer 24.8157 seconds. So this is the time taken for train to attain a speed of 50 kilometer per hour. So still we have the other parameter to calculate, that is the current during the notching up period. So thus we have completed one case, that is the time during the acceleration period. Next, to calculate this, we have the power output from the driving axle. So the power output is nothing but what? Power output is nothing but what? Ft into Vm by 3600. So this we have seen in the derivation part, which is nothing but what? Which is actually the formula for the power output. Hence, we will be using the same formula to calculate the power output, because why we are using this? If I know the power input, then actually I can calculate the current. Hence, Ft will be 1,92,000 and Vm is 50. Hence, I could calculate the power output from the driving axles. So, thus we have calculated the power output, which is nothing but 2,666.666 kilowatt. So then I have to calculate the power input. So to calculate the power input, the efficiency will be given in the problem. You can observe here the efficiency of motor is 85%. Hence I could use this formula to calculate the power input. So the power input is nothing but what? Power output by the efficiency of the motor. Hence it is nothing but 0.85. Efficiency is nothing but 0.85. Hence the power input will be 3137.2549 kilowatt. So power input, we have the formula, which is nothing but voltage into current. I know voltage, which is given in the problem, which is nothing but 3000 volt. Then I can calculate what is the current during the notching up period. So what is I now? Current is nothing but power input divided by voltage. So here, hence the power output in kilowatt, let us convert the kilowatt into watt by multiplying into 1000 divided by voltage, will give you the answer 1045.7516 ampere. So this much amount of current will be drawing by the motor during the notching up of the acceleration period. Hence we have calculated the current also, and also we have calculated the time taken by the train to attain a speed of 50 km per hour. Hence, we have calculated. Let us move on to the third problem. A train weighing 120 tons is to be driven up an incline of 2% at a speed of 36 km per hour. If train resistance at this speed is 2 kgf per ton, find the current required at 1500 volt DC if efficiency of motor and gearing is 88%. If current were cut off, how long would train take to come rest? So you can read the problem and you can understand the dead weight of the train is given, which is nothing but 120 ton, and the gradient directly they have given. So in the like in the earlier problem, they'll be specifying the gradient with some ratio like 1 in 200 or 1 in 3000, like that they were specifying. Here directly they have given the gradient, which is nothing but 2%. Okay, so here we need not to multiply by 100 and all, the gradient is 2%. And the speed also they have given, which is nothing but Vm, which is nothing but 36 km per hour. And train resistance here they have given as 2 kg force per Newton. Please remember, they have given in terms of 2 kg per ton or 2 kgf per ton. But while using the train resistance, it should be in Newton per ton. Hence, we have to convert this into Newton per ton. So that is the one task we have to perform. And the current, and here also we have to calculate the current required if the input voltage is 1500 volt, and the efficiency of motor and gearing, the overall they have given us 88%. And also we have to calculate if current were cut off, how long would train take to come rest? So when we are going to cut off the current, we'll be cutting off the current during the coasting period. That is, as I told you, the train will be running on its own momentum. So therefore, I have to calculate the time T3 here. So that means what? How long would train take to compress means what? We have to calculate the coasting period, which is nothing but T3. So this is the given data and this is the parameter we have to calculate. So first we have listed out the data, and see here we have to convert the kg force or the kg per, usually they'll be given as kg per ton or kg force per ton. So, but we have to convert this into Newton per ton. So how do I convert it into Newton per ton? Because we know that Newton is nothing but what? Force. Force is nothing but what? It is nothing but what? Which is nothing but mass into that is mg, that is mass into acceleration due to gravity. Hence the acceleration due to gravity value is 9.81 meter per second square. Hence we have multiplied with the 2 to get the Newton per ton. So please remember that if they given in kg force per ton or kg per ton, we have to convert it into Newton per ton. So how do I convert into Newton per ton? By multiplying by 9.81 to convert it into Newton per ton. So because 1 kg F is nothing but 1 kg force is nothing but 9.8 Newton. Hence if I multiply the value by 9.81, then I'll be getting the value in Newton per ton. Okay, so this is the thing they have given. So again we have to follow the same procedure. That is we have to calculate the time T3. So how do I will be calculating the time T3? So the tractive effort is nothing but what? Here the 98.1 Wg plus Wr will be the tractive effort formula. Okay, because here the acceleration period we are not interested in. We are interested in only the tractive effort which is required during the coasting period. Hence we are neglecting the alpha value. Hence the 277 We alpha, what we are having that term, so that will be neglected and it will be taking only this term, that is the force required during the gradient overcome gradient, and the force which is required, or the tractive effort which is required to overcome the train resistance. So this will be the data we are taking here. Hence, power output from the driving axle, again we have the formula which is nothing but power, as I told you, it is nothing but rate of work done, hence work by time, or we can write it as force into distance by time, which is nothing but the power output at the driving axle. The formula again is Ft into Vm divided by 3600. So Ft value we have to calculate, that is by substituting over here. So that step I have skipped here. So Ft, what is the formula? This is the formula, that is 98.1 into W is nothing but 120 into gradient is 2 plus again W is nothing but again 120 into R is nothing but 2 into 9.81 will give you the answer 23,784 Newton. Hence the Ft value will be 23,784 Newton. So let us substitute. Hence the power output we have calculated, which is nothing but 237.84 kilowatt. So power input I can calculate from this formula, that is power output by the efficiency of motors and gear, which will give you the answer 270.2727 kilowatt. So this will be the power input. So next we have to calculate the current drawn, correct? So how do I calculate the current drawn, which is nothing but V into I. Power is nothing but V into I. I is nothing but power by current. Sorry, power by voltage. So hence power input in kilowatt should be converted into watt, that is into 1000 divided by 1500, which will give you the answer 180.1818 ampere. So this is the current required. And we have to calculate the time T3. So how do I calculate time T3? As I told you, in the coasting period, we are not going to put any effort, or we are not going to provide any power. Hence, the tractive effort will be 0 during the coasting period. Please remember that. So if we are talking about the coasting period, during the coasting period, the power input or the tractive effort will be 0 and the train will be running only on its own momentum. Hence, the tractive effort will be 0 during coasting period, and let coasting retardation will be beta C. And we are assuming that WE, that is the effective weight, will be one greater than dead weight, that is 1.1 times greater than the dead weight. So the formula will be changing in this way. That is, the tractive effort is nothing but 277.8 WE alpha. That is, instead of alpha, we are going to substitute the coasting retardation, and this is retardation usually in the decreasing order. Hence, we'll be using the negative sign here. Hence, it will be replaced by negative sign, that is minus beta c, and the remaining all terms will be remaining same. Please remember, during coasting period, tractive effort is 0, as well as the acceleration should be replaced by retardation, and the sign we'll be using here is negative sign. So let us substitute. Ft is 0 and we have to calculate beta c. So why we are doing this steps? Why? Because so we have to calculate the time t3. So time t3 is nothing but what? It is nothing but beta c divided by alpha. Beta c divided by speed. Hence we are calculating this beta c value. So upon rearranging and all, and please remember that WE will be replaced by 1.1 W, and W will be remained as it is, or sorry, W we know that is 120 tons. So let us substitute the data, or we can do in this way, because W is term is present in all these three terms. Let us take W common, and if it is sent to LHS side, then it will also become 0. Hence W is cancelled over here. Hence remaining terms will be rearranged, so that beta c is nothing but 0.7062 kilometer per hour per second. Then we have to calculate the time taken to come to rest, which is nothing but speed by beta c, or speed by retardation will give you the answer 50.97009770 second will be the coasting period. So this is the time taken by the train to come to rest. So you can observe here, within this small span of second, or like within 1 minute, the train come to rest. So this is how we have calculated. Okay. So this is how we have calculated. So next we'll move on to the next problem. An electric train accelerates uniformly from rest to a speed of 48 km per hour in 24 seconds. If then coast for 69 seconds against a constant resistance of 58 Newton per ton and is brake to a rest at 3.3 km per hour per second in 11 seconds. Calculate acceleration, coasting retardation, scheduled speed. If the stops are 20-second duration, what would be the effect of scheduled speed of reducing the station stops to 15-second duration? Other condition remaining same. Allow 10% of rotational inertia. You can understand here the speed they have given, which is nothing but 48 km per hour, and the train is accelerating uniformly from rest. That is, they're talking about the acceleration time. So usually the acceleration time, and to reach the speed of maximum speed 48 km per hour, the train requiring is 24 seconds. If then coast for 69 seconds, that is the coasting period time T1 they have given 24 seconds, VM is 48 km per hour. Coasting period they have given, which is nothing but T3, which is nothing but 69 seconds. And the resistance they have given 58 Newton per ton. Again, they have given in Newton per ton, need not to convert again. And it is brake to a rest of 3.3 km per hour per second. That is the coasting retardation they have given, that is beta c is nothing but braking means what? It is nothing but coasting period or retardation period. So again, beta c will be 3.3 km per hour per second, and time t3 again they have given, which is nothing but 11 seconds. We have to calculate the acceleration, coasting retardation, and the scheduled speed we have to calculate. So here this is what they have given. It is nothing but the coasting beta c they have given, and we have to calculate all these data. Okay, beta they have given, and we have to calculate beta c and the scheduled speed. Okay, so and the stopping time also they have given, which is nothing but 20-second duration. So let us list out the data. Time T1 is nothing but 24 seconds. Time T2 is nothing but 69 seconds. If then coasts for a 69 second, that is a free running period, which is nothing but coasting period is nothing that is nothing but 69 seconds. and T3 is 11 second. V1 is nothing but 48 kilometer per hour, and the time stop is 15 second. And the time, so to calculate effective weight by allowing 10% inertia, it will be 1.1 W. So let us go with the problem. First, we have to calculate acceleration. Acceleration is nothing but alpha. So they have given V and V1 value, which is nothing but Vm again. So therefore, V1 by T1 will give you the answer, that is speed by time will give you the acceleration. Hence, I could write this formula, that is alpha is nothing but V1 by T1. 48 by 24 will give you the answer 2 kilometer per hour per second. Let coasting retardation be beta C. So again, we have this formula, Ft is equals to 277.WE. Instead of alpha, I'll be replacing by minus beta C, and 98.1 Wg plus Wr. As I told you, during coasting period, tractive effect will be 0. So let us substitute, and hence you can calculate the beta C. So what is beta C here? Upon rearranging, again W will be cancelled out, and it will be beta C will be 0.1898 kilometer per hour per second. So next we have to calculate what is the speed at the end of coasting period. That is nothing but V2 we have to calculate. V1 they have given, and V2 we have to calculate. How do I calculate V2? Because beta C is nothing but what? It is nothing but V1 minus V2 divided by T2. So we have this, yes, V1 minus V2 divided by T2. Then upon rearranging, I could get this formula. That is, I'm interested only with V2. V2 is nothing but V1 minus beta C into T2. So we have V1, beta C and T2, substitute all the value and you'll get the value. V2 is nothing but 34.9038 kilometer per hour per second. Per hour. And we also have to calculate the distance traveled. So the distance traveled is nothing but what? Again, this is the formula we have derived in the quadrilateral type of curve. That is, distance traveled formula will be this formula. So again, I'm using this formula because I know V1, V2, T1, T2, T3. So let us substitute all the data. Hence, you'll get the distances 1.00782 kilometer. And scheduled time. So what is the scheduled time? So the scheduled time TS is nothing but what? It is the time for free run plus the duration of stop, that is stop time. Time for free run plus stop time will give you the answer of this. So the capital letter T is nothing but what? It is the time for free run. So the time for free run is nothing but what? The time for run. So the time for run is nothing but what? It is the time during acceleration, time for free run, and time for coasting period. If I sum all these three, then I'll get the time for total run. So then this will give you the scheduled time. So which is nothing but 124 seconds. And we have to calculate the third term, that is scheduled speed. So how do I calculate scheduled speed? Which is nothing but 3600 d by Ts. So I know Ts, I know distance d. So substitute, I'll get the Vs, which is nothing but 29.25929 kilometer per hour. So this is how we have calculated the data. So in the next video, we will be solving some more problems related to this. Thanks for watching the video.